All right, go ahead.
Okay, is this working?
Yep, 1 second. Let me just go full screen here. Okay, go for it. Thanks.
Okay, so thank you for having me remotely, and I'm sorry I cannot be there in person. So I'll try to stick to the half-hour slot. I'm going to tell you about neural encodings and their scaling laws. And so this work and the papers I will talk about is work that's been done in collaboration with Florentin Guth, who is a postdoc at NYU and the Flatiron Institute. Okay, so in the previous talk, Victor compared neural networks to quantum computers. I'm going to use a different comparison, which is a much more modest one. I'm going to compare neural networks to steam engines. And I think we have a lot to learn from the history of steam engines in order to better understand neural networks. So this is showing, a collection of different types of steam engines from the 19th century. And back then there was a zoo of different architectures, and engineers were trying to optimize them by trial and error. Some of them were quite sizable, like the one shown here. But if we look at the history over the past 200 years, okay, what has happened is that the architectures of engines have evolved a lot. And I just mentioned several of them here. There are many more types out there. But interestingly, what it took to go from one architecture here to the next was not proceeding by trial and error. It really took having an understanding of the background theory. Okay, and so historically, people had to understand first the difference between temperature and heat, the different forms of energy, and then entropy to come up with the laws of thermodynamics. And it's only at the point when people had this theoretical understanding that it was possible to basically move very far away in the space of possible engines and come up with fundamentally different architectures and much better efficiencies. And so one question I have is, where are we today with neural networks? If we imagine a similar axis, are we much closer to the left, or are we already far away on the right side uh, of this axis? And if we can understand how to answer this question, we can also ask the same question for biological brains. And I think it would be very interesting to try to get an idea of, where biological evolution is along that axis and where it could go potentially. So I'm going to try to bring some elements of answers to these questions by trying to address, how does a neural network learn and what does it learn? In order to do so, we can look at neural networks at different levels. We can consider the output of the network, basically their statistics through the loss, the activations or the weights, and there are different words to also refer to these quantities, either the performance, the representation of a given input, and at the deepest level, the encoding. Okay, so what is the weight structure that has emerged when a network is trained on a given data set and task? So there are these three levels. That's how I see, three different levels at which we can study networks. And there are pros and cons with each of them. We look at the loss. I think you all know that. Basically, by definition, we want to minimize the loss on a training set. And at the end of training, we typically get two numbers, a loss for the training set, a loss for the test set. And because we only get these two numbers, basically, in a way, that's a poor, it's a very limited information on what's going on. Okay, still, people have been able to come up with interesting scaling laws, the famous Kaplan et al. Scaling laws, on how the loss depends on compute data set size or number of parameters. But because those scaling laws are so simple, they are scale-free distributions, again, we don't have much to understand what's going on internally. So what I'm going to do today is to show you how to try to answer these questions about how much is learned, what is learned. I'm not going to talk about the loss at all. I'm not even going to look at the activations. I'm going to go as deep as possible and try to understand the weight structure that emerges during training in these networks. The results I'm going to present are described in these three papers. The last one is about to be online. So I'm a physicist, and what we do as physicists, we try to extract the essence of a phenomenon. And to do that, often we design experiments to simplify what we see. And so in this case, here's the setup I'm going to use. I'm going to consider classification on ImageNet. So that's a very generic task that many people study. And I'm going to consider CNNs, but very simple CNNs, CNNs with depth-wise separable convolution, which means that the weight tensor at every layer is going to be factorized in a spatial component and in a channel component. And I will not have enough time to go into all the details, but basically most of the action is in the channel space. And so the essence of what I'm going to do is the following. What I would like is to extract the size of the encoding. So what is the dimensionality of this weight structure that has emerged during training and study it. In order to do so, I'll just give you the flavor of how we are going to do this. I will not go into the details, but it's all explained in those papers. We are going to operate through that following track. We basically look at the weight covariance structure. We look at its spectrum. We do a signal-to-noise decomposition. And from that, we extract a characteristic scale. Okay, and so what I'm going to do now, I'm going to show you basically what we find to convince you that this is actually a meaningful approach. So here is one first example. On the left, we have three images of ImageNet. So that's the original ImageNet data sets. And next to that, we have different modified versions of ImageNet. So let's start with the original version of ImageNet on the left. So we train this CNN to do classification on ImageNet. In this case, we do a simple setup. We just consider 10 classes. And what we do is that at each layer of the CNN, we can extract the encoding dimensionality. So the dimensionality, the meaningful dimensionality of the subspace of the weights. And this is what we find. So I'm showing here this encoding dimensionality as a function of depths. Okay, and we are using for this task a network that has 5 nonlinear convolutional layers, and layer 6 is just a classifier. So this is what we find. Okay, so this is now the encoding dimensionality that has emerged during training inside this network. This quantity is defined such that at random init, or if the network does not learn anything, this is 0. Okay, so this is an excess above random. And what is very interesting to see is that at each layer, the network has learned more and more meaningful dimensions or more and more features if you want. The last part, the drop, is by definition what is expected. That's the job done by the classifier. That's just a linear projection onto the number of classes, -1. So the interesting part is this rising part here. And so what we can see here is how many features or how many dimensions in weight space have been learned in order to perform this classification on ImageNet. And now what I can do, I can look at how much needs to be learned by networks trained on these different versions of ImageNet. Okay, so here we shuffle the pixels on small scales, and we use the same random shuffling for all the images. Okay, here we do a shuffling on intermediate scales, so we preserve the small scale structure, but we randomize the rest. And in the last version, we basically we shuffle all the pixels. Okay, and again, it's the same random shuffling for the entire data set. And the neural networks can learn these kind of data sets very easily. I would like to point out that if we as humans were given the data set on the right, it would be almost impossible to say anything meaningful about this classification task. But neural networks can do that. And we would like to know how they manage to do that and how much they need to learn. So we repeat the same type of measurements. We extract this encoding dimensionality as a function of layer, and this is what we find. So for the data set that's been perturbed on small scales, we see that this network is going to learn a bit less in the first layer, which corresponds in CNNs to the smaller scales, and then a little bit more, and basically for the rest, it's roughly the same. Okay, and that makes sense because the large scale spatial information is basically preserved. But interestingly, we can also see what's going on for the other types of random shuffling. And in this case, we see that networks manage to perform the task, but they have to learn much more. Okay, so the y-axis is log scale. So in order to perform the task with the fully randomly shuffled pixels, the network needs to learn 10 times more features to perform the task. We can continue with examples that are even more controlled. And so here I'm talking about Gaussian random fields. And similarly, I can consider Gaussian random fields with different spectral slopes. And we can similarly see how many dimensions are learned. And what we can see is that the number of dimensions learned here basically does not depend on the slope of the power spectrum of these Gaussian random fields. And for those who are familiar with random labels, we can even answer the question about how much is learned to perform random label tasks. And this is shown as a dashed line. I'm happy to answer more questions if you like on this topic. Okay, so that's the summary, and I hope this gives you a flavor already and convinces you that we have extracted a meaningful quantity here, and we can meaningfully tell how much has been learned at each layer. This goes, basically as we would expect for many types of experiments. I'm going to give you a second example now. I've been talking about ImageNet, and if you're not familiar with ImageNet, is there a question?
Question, go ahead. How does the classification? Did you hear the question?
No, I did not hear.
How does the classification accuracy change as you scramble?
How does the classification accuracy change as you scramble the images?
So it goes down a little bit, but in all the experiments I'm presenting in this talk, the classification accuracy is always what we call good enough. So we are not trying to maximize it and get state of the art, but we are always in the regime where classification accuracy is something like, I don't know, 80% or something like this. Okay, so it's always good enough, but I'm not trying to like maximize it. And of course, when the task is harder, there will be a tendency for the classification accuracy to go down a bit, but we are always operating in a regime where the classification performance is good. Okay, there is no failure mode in any of the things that I will present today. Okay, so let's continue with ImageNet. So the structure of the classes in ImageNet is not random. The classes in ImageNet come from another dataset, which is WordNet. Okay, and so the classes in ImageNet have semantic structure. So WordNet is a semantic dataset that was compiled in the 80s by hand, and you can get, an idea of what it looks like on the right here. And so the classes of ImageNet were taken as some of the leaves of this tree. So one question we can ask is, can we recover the structure of WordNet from ImageNet, and more specifically from a neural network that's been trained on ImageNet? Okay, and I'm going to show you that this is actually the case and how to do this. So what we are doing here, we are performing a classification task using just pairs of classes. Okay, so I'm going to take a dozen pairs of classes, and for each of them, I'm going to train my CNN to perform a very simple binary classification task on these sets of classes. And for each of them, we can look at the encoding dimensionality, so how much has been learned as a function of depth. And so this is what we find. Okay, and again, the last layer here is a classifier, so this is just a final projection. So what is interesting is the rising part here. And what we see is that there is a range of sizes. So for some classification tasks, the network needs to learn much less than others. And so this is a factor 3 here in the number of dimensions or features that need to be learned, which means that some classification tasks are much easier, okay, than others. So for example, classifying cats and dogs is harder than classifying cats and airplanes. Okay, and so it's going to depend on their level of similarity. What is very interesting now, so this is just using the images of ImageNet and these pairs of classes. And we use those pairs to basically sample the ImageNet data sets. Now, what we can do after the fact, we can basically ask, what is the semantic similarity of these pairs of classes? And so what I'm doing now, I'm going to color code these results this is after the fact, by semantic similarity, and the semantic similarity is measured simply from the semantic tree that I showed you previously. And as you can see, there is an almost perfect correlation between semantic similarity and the encoding dimensionality that the networks come up with in order to perform these classification tasks. So what we find here is that there's basically a mapping between similarity in semantic space and similarity in this neural encoding space. And we have now the tools to basically read this encoding similarity in weight space directly. And what we see is that it carries the underlying structure of ImageNet that came from WordNet. So I hope this second example again basically convinces you that we have been able to extract a meaningful encoding dimensionality here. If we repeat the same operation using activations instead of weights, this is what we get. Okay, and so in this case, we no longer see clearly the difference between the different semantic similarities. Okay, and so this highlights the fact that the structure of what's going on in activation space is very different from what is going on in weight space if we just read things from at the covariance level. And so in activation space, basically what we see, this is just a manifestation of the size of the layers. That's it. Okay, it's much harder to read this type of information in activation space. The key is in weight space and it's directly accessible there. Okay, so I've told you about ways to quantify how much is learned with neural networks. And now I'm going to go to the next step and try to say something about what is learned. And so here, a big question that I had for a long time is that if we take different neural networks and we train them to perform the same task, are they going to do it the same way? Is there one unique best solution to perform the task? Or will they do it in many different ways? Okay, are there many different types of solutions to perform a task? So we can try to answer this question here. And so to do so, the key is to basically compare two neural networks, pairs of neural networks each time trained on the same task. So in order to do so this is just a schematic a pair of neural networks. Let's see how to approach the problem. We can take two networks with different random inits. We train them on the same data set and task, and then we look at the weights. If I focus on the first layer of these two networks, I can look at the weights, I can look at the structure of the covariance, and I can look at its eigenvectors, and I can compare the eigenvectors learned by the two networks. And if I look at a cosine similarity between these eigenvectors, this is typically what we get on a standard classification task. So what you see here, the x-axis is showing the rank of eigenvectors for the weights of network 1, and in the y-axis, same thing for the other network. And I'm showing the absolute value of the cosine similarity here. And what we can see is that these two networks basically learn very similar features at layer 1. And this has been known for a long time. It's also possible to even visualize, for example, the spatial patterns that the first layer is learning in each case and show that they are similar. Now, if we move to layer 2 and we repeat the same type of measurement, this is what you get. You basically do not detect any correlation between the eigenvectors learned by the two networks. And in many ways, this is the origin of the black box effect. Okay, the point is that as soon as we go beyond layer 1, we can no longer easily track what is learned by different layers. So this is only an apparent problem. If we look more carefully at it, and if we try to understand why, we can notice that what's going on in the first layer, so in the first layer, everything is expressed in a basis set that is given by the input data, by the pixels. And the pixels, in both cases, are ordered in the same way. Now, when we go to layer 2, the weights of layer 2 are expressed in the neurons of the first layer. And this is basically a random basis. It's not going to be the same for network A and network B. And so things being expressed in random basis basically lead to zero correlations when we compare them. There's a way to counteract these random rotations. We can actually estimate them. And we can basically undo them. Or what we can do is that we can align one network with respect to the other. And only at this point, it's possible to meaningfully compare the eigenvectors that they learned. And this is what we find. Okay, so now this is at layer 2. We see that there is quite some correlation between the eigenvectors learned by these two networks after we perform this rotation. Is there a question? I thought I heard something. Okay, so I will continue. We can go beyond that, and we can also ask, okay, so we are seeing two different regimes here. So for over a range of ranks, we are seeing correlation. And beyond that, that correlation disappears. So what is going on? Is it that then they learn features that are different? Or is this part completely irrelevant? So what we can do, we can look at the performance of these networks as a function of maximum rank. So we can do a clipping operation on these ranks and see how they contribute to performance. And this is what we get. What we see for these two networks is that most of the performance, almost all of it, is coming from this lower dimensional subspace where we find correlations between two networks. Okay, so in other words, these two networks do perform the task in the same way. And we are also learning that it's only a fraction of the weight space that does contribute to this performance. The rest is irrelevant, and I can clip my weight space at those ranks without losing performance. So this was a very simple comparison just for one layer. I'm going to generalize this now. We can take two different networks. And so this is a representation of two networks with their different layers. The first layer, which is shown in red here, by definition is aligned because in each case it sees the data and the data is presented in the same basis set. But the other layers are not. They are affected by this random basis. So if we apply this alignment procedure, if we rotate them into a common basis, we can actually compare networks as a whole. Okay, and so this is what we've done. We take two networks, we align them, and then we compare what they have learned. This is a first example showing what happens if we take two networks with different random init. And so those are just two CNNs. They have 5 layers trained on ImageNet, very classical approach. And what we see is that at all layers, we find a very high level of similarity between the eigenvectors found in weight space. We can compare two networks with different widths. This is what is shown here. And the result is the same. We see that, despite having different widths, so in this case, one is 10 times wider than the other one, they learn similar features. We can take different networks, train on different sets of classes of ImageNet. So one network is learning on 50 classes, the other one on 50 other classes. And so here it's important to realize we are talking about two disjoint data sets, two sets of natural images, and we find again a high level of similarity in what has been learned. So the message here is that there's quite a high level of similarity or even universality in learning. It's that different networks with different random init, different widths, train on different types of data, as long as we stay in the same universality class of data sets, we learn very similar features. And so what we are seeing here directly at the level of the weights is the reason why things like transfer learning, for example, work. Okay, it is because of this universality in learning. Okay, so I showed very briefly that we can quantify how much is learned. We can say something about what is learned, and we basically find some universality there. And to finish, I'm going to now look at some scaling properties of what is learned in weight space. Okay, so this is another experiment to give you a flavor of what happens internally when we vary the width of networks. So it's the usual classification task on ImageNet. For simplicity, it's only 10 classes here. And I'm showing the encoding dimensionality as a function of depth. Okay. The last layer is the classifier, always. So I start with a narrow network. And I'm showing here, the encoding dimensionality that emerges during training. But at the same time, I'm also showing with this dashed line the capacity of this network. Okay, and so this is a very narrow network. And what we see is that then basically during training, the network is trying to build a structure that is as high dimensional as possible, and it's limited, it's bottlenecked by the size of the architecture in this case. If I take a wider network, we see that more features will be learned. And again, it's bottlenecked by the architecture. And so I can keep increasing the width of my network each time with another factor 2. And I see that each time the encoding size increases. But if I continue to increase the width of my networks, we reach a regime where the story starts to change. This is 10 to the 8, 10 to the 9, 10 to the 10, 10 to the 11, and 10 to the 12. And we see now that over a wide range of widths, there is a pileup of this encoding dimensionality. So in other words, we can basically find two different regimes here. There is one regime of network width when what is learned is constrained by the width of the network. Okay, and so the encoding that emerges is basically architecture constrained. Then there's another network. There's a width beyond which what is learned no longer depends on the width of the network. We call that the free encoding regime. And this is the more interesting regime, okay, because we can now study the weight structure that is learned, and that's a function that no longer depends on the width of the network. And the results that I presented previously, they were all in that regime, in the free encoding. So it's interesting and important to realize that there are these two different regimes, and depending on where we are, we will get different results. And the most interesting regime is the free encoding regime, because we can say something that is much more fundamental about the data and the task. Okay, so this is one example of two networks illustrating this effect. On the left, we have a very narrow network. And what we see is that when we train on different number of classes, okay, so in color here, I am varying the number of classes, or basically you can think of this as data size. In all these cases, the dimensionality of what is learned is the same. And because we are bottlenecked by the architecture, we are saturating here. But now if I take a network that is much wider, and so you should appreciate that the y-axis is log, then we start to see differences in how much is learned depending on data size or the number of classes. And I'm going to go deeper into that now and to show you basically what that means. Okay. So what I'm presenting here are phase diagrams of weight space inside CNNs. Okay, so I'm taking my usual 5-layer CNN, so 5 convolutional nonlinear layers. I'm not showing layer 1, it's very similar to layer 2, just for clarity. And so let's look at the axis. So the x-axis here is the width of the layer. And I can basically, so I have a scaling parameter to increase the width of all my layers, so all the same way. And the y-axis is the number of classes, but that's basically a good proxy for data size. Okay, so this is width, basically number of parameters of the model, and the y-axis is data size, number of data points. And what is shown in color in this 2D plot is the encoding dimensionality that we measure. So I need to maybe briefly mention that in order to come up with these phase diagrams, we had to train hundreds of models. Okay, so at every coordinate here, we have a different network trained on a different amount of data. So this is a summary that comes after having trained hundreds of models. What we observe is quite interesting. We have two different regimes. Okay, so when the width is narrow, what we learn because of the verticality of the contours does not depend on the amount of data. And as the network gets wider, the orientation of the contours here changes and it goes from vertical to horizontal. And here we are in a regime where what is learned is no longer a function of the width, and it's basically a function of the data. Okay, and so we have these two different regimes called A and B here that are fundamentally different. In regime A, the learning is bottlenecked by the architecture. And in regime B, we are no longer bottlenecked by the architecture, and the limitation becomes data size. Interestingly, if we have a closer look at the structure of these learned weights, we find that the spectral properties of the weight covariance is different between regime A and regime B. In regime A, the weight spectra are exponential with a characteristic scale that is defined by basically the size of each layer. But in regime B, in red, we see the emergence of a parallel tail, which basically shows that something qualitatively different is taking place during learning in this regime B. I will just give you an overview of all of that, but I can answer more questions and we will present more details in the paper. But what is interesting also is the realization that this transition here between these two regimes coincides with the double descent phenomenon. So on the right here, I'm showing test loss for all these different models. And what you can see here, this feature here is the peak of the double descent. Okay, so the double descent regime is basically in regime B here. If I take some cuts of these 2D diagrams to see what happens more clearly in 1D. So this is the test loss, and this is double descent phenomenon. Okay, so the test loss goes down first. It goes up, reaches the peak, and then it starts to gently go down. That's the double descent. Now, if I look at similar horizontal cuts in my phase diagrams for the weights, we see that the dimensionality increases up to a point, and then it starts to plateau. And the departure between the increase and the beginning of the plateau phase is basically the scale of the peak of the double descent. Okay, so what is very interesting here is that we are starting to have an internal view of the double descent phenomenon inside neural networks. Okay, double descent is basically a property of the test loss, but now we can see internally how this takes place. Okay, so we have looked at these dependencies in one direction, and now let's look at them in the other direction. Okay, so let's look at the vertical dependencies here, and that's one of the most interesting scaling, I think, that we can see in the internals of neural network. So what the lower panels are showing here are the encoding dimensionality as a function of number of classes or data size. In each case, the color refers to the width of the network. So at the bottom, we have very narrow networks, and we see, as you now understand, that when the networks are narrow, what is learned is bottlenecked by the capacity of the network, and so it does not depend on data size. But as we keep increasing data size, we reach this point where what is learned by the networks no longer depends on the width. So the width the capacity can be much, much greater. And it can have any value here. The networks always learn the same amount. Okay, so there is a pileup of all these curves, and the slope of this envelope is shown here with the dashed line. We can see that these dependencies are parallel distributions. Okay, so they are scale-free. The index of this, which is how much more we are learning as we see more and more data, is a very regular function of depths. Okay, at layer 1 is 0.1, layer 2 0.2, etc. And then we notice a jump in this exponents. It goes from 0.4 to 1. The last exponent value here is actually not anecdotal at all. 1 is the maximum rate at which we can expand dimensionality. Okay, so this encoding dimensionality is basically the effective number of parameters used internally by the network to perform its task. And so if we think of this in terms of linear regression, the fastest rate at which we can infer parameters is when the number of parameters is proportional to the amount of data. This is exactly what we find here in the last nonlinear layer of this network. Okay, so this is fascinating. We are seeing a buildup through depths. As a function of depth, we are seeing a buildup, a hierarchical weight structure that is emerging. It's emerging at different rates in a way that is very regular. And for a network that is well adapted to the task, the last layer learns at a rate for which the encoding dimensionality is proportional to the amount of data. And we can explain why, and we can say much more about it, but I don't have time today. So I mentioned that we have this interesting scaling laws with the loss, but if we study the weights, we have a much richer view of what's going on in the network. And what we can see here with this neural encoding scaling.
Bryce, I
Yes.
apologize. Can you wrap up in the next couple of minutes?
Yes, that's the that's the almost last slide. Yeah. So we have this much richer view. We are seeing that there are basically different learning rates at which networks develop their internal encodings as a function of depth. There is a hierarchical structure that emerges internally. And for a network that is well adapted to the task, there is a very nice property that this encoding in the last layer has a dimensionality that is proportional to the amount of data. Okay, and so this is a much deeper and richer view of these neural scaling laws because we are starting to be able to say much more explicitly what is happening internally and why. Okay, and so I'm wrapping up here. I started with these questions. And what I showed you is that we can actually meaningfully quantify how much is learned, and we can compare that for different data sets. We can say something about what is learned and show that different networks end up learning similar features or weight space eigenvectors. And finally, we can look at the scaling properties of all these quantities, and we find very regular, very interesting structured hierarchical neural encoding scaling laws. And I'm going to stop here, and I'm happy to take questions.
See, I don't see Elliot. Oh, there you are. Okay, so whilst Elliot is setting up, if there are any questions, I will try to retranslate them into the microphone. Yeah, go ahead if you're on Zoom. Yeah, I guess I have a comment or maybe a question. It seems to me that whatever your empirical sort of studies are going to observe is a property. I guess it's not clear to me whether how much of that is a property of a data set that you're studying versus the property of the architecture that you're studying. Is this some, is there a way to distinguish?
Yeah, that's right. So what I mentioned is that we find two different regimes. We find a regime where networks, what networks learn is a strong function of the architecture and the width.
Right.
But if the capacity is sufficient, then what is learned is basically just a function of the data and the task. Okay, and that's the more interesting regime, I think, if we want to study what is learned. And yeah, so it's very interesting and very important to distinguish these two different regimes. And so, the answer to your question is it depends on where you are in these phase diagrams.
Right.
Okay, so, and I would like to point out that, if we look at the literature and people using CNNs to study, to classify ImageNet, most of the networks that are used in the literature, they are in this regime A. They are actually bottlenecked by the architecture. You need very wide networks to go to the other regime and reach these free encoding regimes where what is learned becomes a much purer function of just the data.
Right. I think Victor stepped out, but somehow, it wasn't planned this way, but it seems like what you presented and his more a microscopic description of the number classification, there may be some connection that there may
Yeah,
be
absolutely. I'm planning on reaching out and yes.
Okay. All right, great. Thanks. Let's thank Bryce again. I'm just worried about lunch at this point. I guess it doesn't matter what we
do. Okay. Okay. Hi. Yeah. So my name is Elliot Paquette. I'm very happy to be here. Thank you for the opportunity for putting this together. Yeah. So I'm going to talk about something very related. So it's going to be about two things. So something about a solvable model of scaling laws. In fact, the very loss curve laws that you saw, and then a story about covariance spectra. So we'd heard about weight matrix spectra and activation spectra and dimensionality just now. So I'm actually going to talk about activation properties as you go through the network. And so just we've heard this a few times, but this is the context for this. So there's this very nice Kaplan scaling paper with these wonderful pictures and these measured relatively, as we've established, shallow sloped power laws, but that extend over a very long range. And the goal, I mean, okay, you've heard this a couple of times now, so I'll just go quickly through this. I mean, I would say, to me, it's a very interesting paper, by the way. If you haven't read it, it's filled with all sorts of stuff. You can read it quickly, and there's all sorts of claims in there. Like, I think like half of them are true, but it's a very inspiring paper. Like, so it can lead to a lot of good things. So its impact is far higher than the truth for percentage. Yeah.
Thanks, by the way. I haven't needed the encouragement to read it, but unfortunately, Cengiz is not here. I was a bit confused when he gave us this overview yesterday. He went, and I kept like being bothered that the power of these exponents is so shallow.
Yeah.
And then at some point he sort of had exponents which were quite a bit larger.
Yeah.
I was gonna try to understand how that happened. Can you comment on that, or if that's a distraction?
So right. So depending on you set this up, there are different exponents you can. I mean, okay. So I can't quite bridge from point 1 to point 3, which is what they end up in this other influential scaling paper, Hoffman et al. So I don't actually know why it's such a big gap.
Like 0.3 is kind of like reasonable exponent.
But there's quite a big change in setup in how you do. Like, there's a lot of decisions being made under the hood on how you get these laws, and all of those changed in the second paper. So I think that's part of it. But these are pretty shallow laws. That's right. But I would say that to me, there's two super important questions about this. Can you make a model and understand what gives rise to this exponent? Is there anything you can do to control this exponent? Or is this exponent for a given problem a fact of life that you can't change? I mean, obviously you can change it to some extent. So there must be some things you can do. But to what extent can you change the exponent? And then the other question, and this is almost propaganda, because the real question is, when does that stop, right? There has to be some saturation at some point. So the question is, when does this stop? Do you know when it stopped, and what do you do when it stops? Is there something else you can do? So those are $2 billion questions that are going on with this. Can you change the exponent, and when does it stop? So I'm kind of going to be focused on the first one. I want to look at a solvable model, and I want to look, in fact, my goal is to look at an optimization algorithm on that, and to understand the role of optimization algorithms on that, and to what extent that actually influences that exponent. Okay, so I'm going to introduce a model. It's not my creation. This is going to be a very simple way to create a model where you can say a lot about it and compute those exponents, and it has some kind of relationship to reality. And there's, of course, many ways in which it's not, and I want to discuss that a little bit. So the idea is I'm going to imagine that there's some perfect world and some perfect data vector that's out there, and that we don't have access to it. So there's an unknown space. It's large. You should think of V as being, in principle, infinite dimensional. But in fact, in some cases, I can't do that. That won't make mathematical sense. So there's a large dimensional space, and it'll eventually be a Gaussian data vector there. You don't have access to it, so what you do instead is you embed it somehow. And the embedding here, I'm going to imagine a very simple sort of neural network inspired embedding, which is that you multiply it by a random matrix. This is this weight matrix. It's not an interesting matrix. Of course, we know that as you train these become interesting, and that's an important limitation of this. But in any case, this is just a Gaussian matrix. The important part is that it takes it from high dimensions down into small dimensions. So you take it from V dimensions down to D dimensions. I'm going to then apply an entry-wise activation function. So So that sigma is some sort of nonlinearity. Now, at the same time, I want to compute, I want to have a target. So the target is going to be that there's some in the latent space, there's some beta hat, some vector, interesting vector that I'm interested in. So this is a single task problem. It's up there. And I have access not to beta itself. I have access to X inner product beta hat, and then potentially filter through some other nonlinearity. And my task is from these observations to estimate in the linear model this. So I'm going to try to fit theta inner product this W transpose X. So here there's I probably won't end up having time to talk about it. So the main algorithm is the most simple one. It's one pass stochastic gradient descent. It's where you sample a new data point and you make a gradient step in the direction of minimizing the squared loss. What would be interesting, hopefully I have a little bit of time to mention at least one other thing that you can do. Okay, so without further specification, this is called a single index model. There's a lot known about it. The key difference, which I'm going to explore here, is that I'm going to put in a slightly more interesting distribution on X. So X is not just going to be isotropic; it's going to have some kind of structure, and that's going to be that it has a covariance which decays in a power law fashion. So because everything is Gaussian in what I'm doing, I don't care that it can be diagonal. So sigma is just going to be a diagonal matrix. And I'm going to have that the diagonals decay like j to the -2 alpha. This is often called a source condition, and there's a large literature about it. This is a real thing. I'm going to show you some measurements. You can take all sorts of data sets. You can measure this number. You get all sorts of numbers. There's an interesting story on what the numbers are. Certainly the alpha is a real thing. I mean, the fact, Gaussian is, the real data is not Gaussian, of course. But I need a target also. And so I'm also going to have a power law target. And this is going to turn out to be the right thing to do to be able to parameterize the different phenomenology that I can get. So as I sweep across alpha and beta, I can get different behaviors of this problem in a proper phase plane. But I also, I want to emphasize that it's, to me, it's really fake. Many people have asked me, and I come from a math background, as we're overly literal. What is beta in the real world? And the best answer to that question is there is no beta. So don't, take me whatever seriously, not literally. It's a thing. It helps me understand this model. But there's so many more things going on in real world problems. In particular, they don't have the structure. So don't overfit for beta. That's a great question. So the source capacity language is not mine, and I don't like it, and I'm using it under duress. Yeah. No, I believe, well, that would be rich if I reversed it, but I'm pretty sure that's correct. Is that true? Is it possible? It's possible. It's possible. I believe that's possible. I've reversed it. That's true. Okay, thank you. Okay, so there are lots of other models of this curve of this Kaplan model, of this Kaplan scaling law. This is not the only way to do this. You do not need to put power law distribution on the data to create these kind of loss curves. The most significant other idea that I think there is that you can have many tasks. So this is a single task problem. I have one thing I'm trying to learn. You can have a lot of tasks, and you can actually remove the power law geometry entirely, and you can also reproduce this effect. So I want to point that out. But you could also do this with mini tasks also. I mean, you can have power law data and mini tasks. So you can do that also. So some of these papers went that direction, and then there's other models of hierarchical models, which produce a a richer picture than this, which don't just have power law covariance, but in addition have further structure. Okay, so I wanted to say a little bit about the alpha. Yeah, so it's easy to measure. So we've seen some of these picture data sets. This is me taking the different classes and just computing the covariances of across a data set. So you for each class you create a matrix, and then you compute its eigenvalues. I did it class by class just in case there was something interesting between classes. There's not. They all have this kind of saturated power law look. It's quite clean for at least 100 eigenvalues. The space here is 3000 dimensional, and then it starts to saturate. It's in images, and there's various ways to try to explain why it's in images. It's also in language. So here's a slightly more complicated picture. Let me try to explain what's happening. So this is GPT-2. There's no picture because it's a text set. So this is the FineWeb Edu data set. This is the first block of text from it. So there, if you want some entertainment, that's what we're looking at here. So this is some representation of it. Now, what have I done? So this is the next token prediction. So I'm taking 1,000 basically words, and then I'm looking at the value of the last word, and I'm looking at the penultimate word, the word just before it, and that gives me a random variable that's the distribution of the word before the last one. So I condition on the last one, and now I'm embedding it. So at initialization in this problem, you just embed it as a random Gaussian vector. So you start by assigning to each of these words just a Gaussian vector. They're all independent of each other. And so now I'm looking at the distribution of the covariance of that random vector. And it's according to the, so this is class by class. So I have 100 classes here. Each of these lines is a different class. And what you should be seeing, I mean, this at initialization is basically some kind of bigram frequency picture that you're looking at. So bigram frequencies have power law decay, and you get some kind of slope there. And there's a lot of things going on in words. So there's actually quite a big difference between how you ensemble this. So just to be warning you, if you want to do something like this is where I just average over everything. So I average the covariance matrix over all the realizations of the last word, and then here I do it word by word, and I get something different. The other thing to point out is the number. Well, the numbers are very close to -1. Yeah.
How do you construct this matrix? So you just pick the vectors corresponding to the word created in that product.
Yeah. Outer product. Yeah. So I take exactly. So I make a covariance estimation of the random vector that represents the word before the last. Let's say the last word is the. So that's one of these lines up here. Look at the previous word. I make an average of that covariance. Yeah, exactly. And it's this one. Okay. It's interesting how this evolves when you train it. So this is after training it. So something changes. It changes quite a bit. I mean, the biggest thing is the numbers change quite a bit. So this is -0.6 now, started at -1, now it's -0.6. So something is, I mean, there's a significant exponent change that's occurring. And then you also see, there's multiple complicated things going on. So like you do have some sort of broken power law behavior there also.
Isn't it always like if it's less than -1, does that mean that the trace is infinite?
Yeah, that's super important. I'm glad you brought it up. So the most interesting division in behavior is if that 2 alpha is bigger than 1 or 2 alpha is less than 1. And basically, you can get both of them. And yeah, and the other thing is more attention needs to be spent on 2 alpha less than 1. For the number of papers for 2 alpha bigger than 1 is massive in comparison to the number for 2 alpha less than 1. You do the same thing at the last layer. So, you know, this is a transformer. You're applying these activations layer by layer. It goes through, and you see something like this. Anyway, so this is to illustrate. You have some of these power law covariances. It's kind of everywhere in this model. It does evolve as you train it. Okay, so I'm going to move on to.
Actually, I have a question here quickly.
Yeah.
Can you explain the y-axis? I cannot read the values.
Yeah, all 0. Yeah, that's something got cut off. Let's see. So it's the eigenvalue, lambda j, and what should it have been? It should have been. So this is a log plot. So I mean, okay, but I think it's normalized to be. I think I normalized it to be 1 at the top. Yeah, but I don't. Sorry about that. But it's log axis. Okay, so I wanted to say one thing about the nonlinearity. So there was a nonlinearity in this model, and I have something to say about it. So I want to start with the following question. I want to suppose that you have data which has this power law covariance, and then I want to ask about what happens to the activations when you pass through one layer of a simple model of a neural net. So you're just going to apply a Gaussian matrix to it, and then you're going to apply an activation function to it. And this is not exactly what's happening in a transformer. Something much more complicated is, but okay. So this is what's happening in a simple, fully connected neural net. You push through this power law covariance through a layer of your neural network. And the short answer is that it doesn't change the exponent. So that's, I think, a very important observation. I don't think it's obvious at all. So these are some simulations illustrating that. The point of this, so this is the activation function. So the first picture is no activation function. I'm taking 2 alpha to be 1.33, which matches this CFAR data. I'm applying a Gaussian matrix W, and then I'm applying an activation function. So the point here is that this line is roughly matching the value. Well, first of all, that it's roughly universal. So it doesn't matter so much what the actual distribution of the data was. So here's Gaussian, but here's also some other choices. So there's a Rademacher data here, and also CFAR itself, which was one of the things which had this exponent. So it tends to be relatively universal. So so what can you say about this exponent? I have a theorem. Unfortunately, not on the archive yet, but it says the following: if you take a polynomial activation, monomial activation. So I take this x to the p, and I look at the observed covariance. So this is the observed covariance that you see after applying this activation function. So W is a Gaussian matrix, X is this vector. Here, X is also normally distributed. I look at the expectation over X of this covariance. Then the eigenvalues, which started here as j to the minus 2 alpha bigger than 1, are approximately j to the minus 2 alpha. So there's a logarithm that enters into it. The logarithm has to do with the nonlinearity. So there's a little bit about the nonlinearity that gets preserved, but it's quite small. But for the leading order, what you're really seeing is that this exponent is preserved when you go through this. Yeah, please. They're very specific. They're x to the p. Yeah. Yeah, so exactly. So it's a really interesting question. What happens for general, even smooth things? You do have this logarithmic growth. You could maybe imagine that if it was an exponential function or something like that, you summed it all up, you actually do change the exponent. So there's probably some classes where that's true, but I don't know. Yeah.
The ones that leave the power off,
Yeah.
like that, localize have a higher time participation ratio. Is the same thing happening here? Do you have some insight about those ones?
Well, it's a really good question. So we wanted to do some kind of statistics based off of this, some like test error computations. We're not there yet. My guess though is that it's like that. Yeah. 5 minutes. Okay. Okay. So I'll just show one picture. This is just illustrating what the claim was. So these are the monomials with different slopes. Some people asked about other nonlinearities. It's hard to extrapolate a lot. My guess is that this function, this x squared e to the minus x squared, does change the exponent, and probably these things are the same. So there's probably a class of non-monomial activations which leave the exponent the same. Okay, so I'm just gonna say quickly then, so what can you do with this? So now the point of that part of the talk was, look, you can apply this nonlinearity. What you actually see is that post-activation, you see power law covariance again, and if you're gonna fit a linear model, why don't we just look at the linear case? So I expect that what would happen with the nonlinearity is close to this. So the linear case we can solve for the dynamical behavior of what SGD does on this problem. So I don't have so much time, so I'm just going to say probably the most important thing is this is the dynamics. So if you don't know SGD, this is a single update being occurred. So I'm looking at this stochastic process, and I'm looking at the risk of this curve. And basically, you can use some random matrix theory, and you get to the following picture that does this picture make sense with me skipping so much? Probably not. Yeah, so there's a couple spectra you have to calculate in order to solve for the dynamics. There's basically these two measures. One of them has to do with it's just the eigenvalue measure, the empirical measure of eigenvalues. You have to do a second measure, which has to do with how the target looks in the basis of the eigenvalues. And okay, so basically these are interesting measures, and they have some sort of change of behavior. They have the kind of pure point section. They have a continuous transition to an absolutely continuous part. Each of those parts of these measures contributes a different term to the loss curve, and finally to the scaling law. And they don't always participate. So it depends on what region you are. Depending on what values of alpha and beta you are, you get different participation of different terms. So there's some sort of interesting point where everything's happening, where everything is sort of this. So this would be the eigenvalue j looks like 1 over j, and also the target is like 1 over j. But then there's a large range of other behaviors. And you can have many things participate. The most important ones I point out. So these F0 and FBP, this is like the population risk problem. You're just solving it F0 is some kind of limit risk because you can't actually solve the problem perfectly because you don't actually have the target in your basis. And then you also have contribution, for example, over here, SGD noise can slow you down. So the algorithm is important. So I think I'm out of time. I'll just say in conclusion, so okay, you have this phase diagram, and there are some things that you can do to change the scaling law if you change the algorithm. So there's another algorithm, which is sort of an upgrade on SGD, where you keep a history, a moving average of your gradients. It's called Nesterov acceleration. And if you do it right, you can actually at least on this problem outperform basically out of every out of the box algorithm. Okay, so that's the idea. Happy to take questions if there's time. Thank you.
Yeah, while Kartik is setting up.
Probably outside. But scaling laws been observed.
So it's a yeah. Well, I mean, this is the best two pictures I can suggest. Yeah, I mean, there's definitely a large class of models which were at some point state of the art, which do produce the same scaling laws, but they differ mainly in that they saturate at different points. So like LSTMs at very small scales are basically doing the same thing, but they have a breakdown as you try to get into the 100 million or billion parameter range. And you can fix it. So there's some kind of fix for LSTM, XLSTM, which more or less lets it recover the same kind of laws. But I mean, there's, as far as I know, there's nothing which outperforms. So they're all sort of, you can recover this amount. Maybe you can extend the length of the scaling law, which is really important. But to my knowledge, there's nothing which really beats it.
On Zoom, everything is-
Should be fine.
training curve for the speakers. Get good at it. Which we don't have. All right, go ahead.
Yeah. So hopefully everyone on Zoom can also hear me. Thank you for the invitation. Very interesting crowd. I would like to tell you a bit about my work on understanding neural networks. The word information geometric understanding is alluding to information geometry, which is a subfield of statistics. For the people in this crowd, you can think of it as a differential geometry being applied to the space of probability distributions. And there is various kinds of esoteric things inside the field, but basically it is this. I found these tools to be quite beautiful, quite interesting to understand neural networks. They're quite old, so this began in the 1940s. Cramer-Rao of the Cramer-Rao bound fame began studying statistics with a more geometrical perspective. Why do we care? Well, if you're a theorist, I would contend that there is two big questions in deep learning. The first one is why can we train these networks? They are so large. You want these networks to capture all the variability in your data, so they also implement complicated functions. F of x is a complicated function if f is a neural network. We want them to do very many tasks, so we also feed them on a lot of data. So it shouldn't be easy to fit these networks even. 10-dimensional non-convex optimization is intractable. We do it in millions of dimensions, somehow get lucky time and again. So why can you fit the networks? Very stark question. This is the kind of things that I was doing in my PhD a few years ago now. And the basic summary, I feel I can make a cartoon of like 10 years of papers of mine, many other people's. is that the energy landscapes that we look at in deep learning, they look very different from spin glasses, okay? They look a lot like the Grand Canyon. You should imagine that the Colorado River underneath is the set of solutions. Doesn't matter which part of the river you fall into. Yes, it meanders around, it is not convex, but basically the name of the game here is to climb down the walls of the canyon, escape the little nooks and crevices along the way, which we do with very large step sizes, and just fall down. So this is why, and this is a admittedly very simplistic cartoon of many people's results across the years, but this is why we can train networks somewhat tractably. Okay. The second big question I would contend is why do neural networks not overfit? Very similar paradox. In college, people told you that if you get 25 data points, do not fit a polynomial of degree 50 to it. It will have a lot of wiggles. Somehow we love doing it in deep learning. We don't seem to get hurt. So there must be something that is nice about your problem that allows you to fit without overfitting. And these are the two kinds of questions that we have worked on. Maybe before we proceed, however, we should take a moment to appreciate why do we even care about these questions. It is not as if the practitioners are waiting for the answers. They are thriving way better than thriving without knowing answers to these questions. I think I'll give you two reasons of mine. The first one is as follows. So there is stuff that we've studied in textbooks, we've studied in college, that somehow doesn't jive well with what is going on in deep learning. Basic calculations with linear regression you can do that somehow flout it. So it behooves us to understand why, and that is just for the sake of completeness. I think the second, perhaps more important reason is that the success of deep learning, I believe, I'd like to convince you, is telling us new things about how natural data looks like. Some properties of natural data, power laws that we saw in many talks in the morning, they are known for 200 years. Cauchy or Fourier probably knew about them, but there is some genuinely new things that we are benefiting from, and that is what I believe lies at the heart of what makes neural networks work. Over the years, there is many kinds of theories about deep learning. What makes neural networks most different is over-parameterization, perhaps so much larger than any other model in scikit-learn. So there is lots of papers on understanding how over-parameterization helps. Well, I asked my mom, and she says, if you have 1 billion parameters, you only fit on a few 100,000 data points. Surely there is not enough information to localize all those parameters. So why the heck are they important if you don't even know their values very well? Okay. There is other kinds of theories. Stochasticity is very important. I would make this point many years ago that SGD is what is very interesting in deep learning and important. Well, you can train neural networks with very large batch sizes. LLMs are trained with really gigantic batch sizes. You can even train neural networks with gradient descent, works just fine. So surely SGD and thousands of variants of SGD on arXiv are not the biggest piece of the puzzle. And you can go around the room. I can pick I can nitpick every little parts of the theory. I think what we are missing is really the elephant in the room. The fact that machine learning fundamentally is about understanding properties of the data. And as theorists in machine learning, we have been very, very callous. The first thing that a machine learning theorist does is take the data and throw it out of the window and never ever model the data. So this is what I would really like to convince you, that data underpins most of the properties that you see in deep networks. And yes, architectures are important, how you train is important, and those are decorations. And this is the main part of the puzzle. Okay. I'll show you a couple results. Rubing Yang, who is finishing her PhD in my group, did them. These are about generalization. And here is a plot that we've seen a few times now. Focus on the blue line. These are the principal component eigenvalues of CIFAR10 images. CIFAR10 is 32 pixels plus 32 pixels, RGB, 3 channels, that's 3072 dimensions, and the blue line has 3072 points. I am drawing eigenvalues in the log scale on the y-axis but just linear scale on the x-axis. The previous speaker was plotting the x-axis on the log scale. Bryce before him was plotting the distribution of the eigenvalues, not the raw values of the raw eigenvalues. Same plot, different picture. What is very interesting, however, if you plot it this way, is that the head of the spectrum has a rather different shape. Okay, and then you have a linear decay on a log scale. So these are eigenspectra that we have begun to call sloppy, and I'll tell you why in a bit. If you think of why this kind of a structure emerges, it is somewhat obvious. The head of the spectrum consists of all the salient variations in the data, the cats and dogs and the frogs and horses in the data set. The tail and the mid part of the spectrum consists of intra-class variations, different types of cats, different types of dogs, etc., or simply aberrations that are very rare things that you did not find many times, like the blue dog. Okay, what you can prove is if input data looks like this, and essentially all data looks like this, as we heard many times, text, sounds, tabular data, you name it, it looks, it has a spectrum of this shape. If input data looks like this, then essentially any quantity that you can compute inside a network, the orange line is what is called the Fisher information matrix. It is the curvature of the output of the model. So it's the second derivative of the output of the model with respect to the weights or outer part of the first derivative. The Hessian is the curvature of the loss function, which is kind of a summarized version of the Fisher information. Different types of correlations of activations across different layers, different Jacobians with respect to different logits. No matter which quantitative you put your fingers on, they all seem to have singular values or eigenvalues that have similar structure. They decay very strongly in the head, and then they decay linearly on a log scale. Yeah. The reason, yeah.
Everything in this plot is about the data.
No. This plot, the blue line is the input images. Then we trained a big network on this with about 3.5 million weights with all the bells and whistles. And then the rest of the quantities are computed at the point that we select at the end of training. Yeah. The reason why we call these models sloppy is as follows. So hold one eigenvector on the orange, corresponding to the orange line, somewhere deep down with a small eigenvalue. This is a direction in weight space where I'm allowed to perturb the weights by 7-8 orders of magnitude before I start seeing any appreciable changes in the output of the function. It is the curvature of the output after all, the Fisher matrix. Okay, so this tells you that out of 3.5 million weights in this particular network, about 100, 200 combinations of these weights are the ones that are dominating your predictions, and all the others here are decorations. Doesn't mean that they're not important, but they're decorations. Okay, that is why we call them sloppy. It's like taking clay putty and then putting it on the on some structure, and whatever sticks, the rest of it is useless. Yeah.
How can you make the weights, remove or affect the blue dog without affecting others? And weights don't touch imaging, they touch the pixel. That these low-lying eigenvalues, I know they're typically localized, so they correspond to a rare image.
No. They are these are eigenvalues of the Fisher matrix. The Fisher matrix has size, number of weights times number of weights, not the number of input pixels. So some people think of the Fisher as the curvature with respect to the inputs, but typically it is thought of as the, yeah. So if this is 3.5 million, so the size of the matrix corresponding to orange line is 3.5 million cross 3.5 million. And we computed, in this case, the first 3,000 eigenvalues of that matrix. So one eigenvector is really some complicated combination of the eigenvalue of the weights. Yeah.
So in the vertical, you put the size of the value.
Yes. No, it's just the index. Just the first eigenvalue. This is the 500th eigenvalue. And this. Yeah, I just sorted them by size. Vertical is the magnitude of the eigenvalue. The horizontal is just the index of the sorted array. Yeah. And traditionally, you will see like Tracy Widom kind of plots where they will draw the eigendensity of the eigenvalues, but that doesn't show you all the structure. Okay, so moral of the slide, deep networks are sloppy. They actually have much fewer degrees of freedom than what you would think by looking at them on paper. Here is one application of this, and this is a theorem. This is a I think I like to say it's a 90% of a theorem, because we can prove it for two-layer networks, for infinitely wide networks, for randomly initialized networks. But in general, it's very difficult to control correlations across for more than 2 layers. So that is not why that is why it is not a complete theorem. But we can get some bounds on the spectral decay of different blocks of the Hessian or different blocks of the Fisher matrix in this paper. But here is one application. So I'll tell you about what are called PAC-based bounds. PAC stands for probably approximately correct. In statistical learning theory, people will write down inequalities of the following kind. Think of Q as a probability distribution on the weight space. Little e of Q is the probability that you make a mistake on a test datum when you draw one sample from this probability distribution on the weight space. Okay, so you draw many samples from Q, you draw many samples from your test data set, compute the probability of making a mistake, and that is little e of Q. E hat of Q is exactly the same quantity, except that you are supposed to draw samples from your training set. Okay, and so people will write down inequalities that say probability of the test error is less than the probability of making a mistake on the training data plus some complexity term. And the complexity term conceptually is just a way to think of how many different configurations of weights you could draw from. So this is a KL divergent Q and some prior P. The prior P is not important. It just restricts the domain. So larger the support of Q, larger the set of models you draw from, more the number of samples you need to localize a good model within that set. Okay, so this is a universal inequality. Any Q you can plug in, and that gives you an inequality. What people in deep learning got very upset about is, so these are very somewhat simplistic calculations. Okay, we've known them since the late 80s, early 90s. Nothing wrong about them, textbook exercise. When people began to plug in numbers into these inequalities, somehow for the first time in around 2017, after knowing the theory for 30 years, they realized that because there is so very many weights in a neural network, these inequalities look absurd. The probability of making a mistake on the test data is, let's say, 5%. Training error typically is 0. So E hat is typically 0. The stuff, the square root complexity term is more like 100. And so what these inequalities, and this is a representative of essentially everything in learning theory, say in their at their heart is the probability of making mistake on the test datum is less than or equal to 100. And at that point, you leave the class, right? Today is the drop deadline at Penn. This is when you should drop it. I think this is why there has been a lot of anxiety about these kinds of theoretical questions in learning theory. But the way to fix it is actually rather simple. You just need to appreciate that you're not fitting arbitrary data sets. You're fitting data sets with at least some structure. In specifically, we showed in this paper that if input data is sloppy, then the Hessian is sloppy. If the Hessian is sloppy, then even an analytical expansion of the right-hand side by simply taking a quadratic expansion of the KL divergence using the Hessian will give you a non-vacuous analytical bound for generalization. Non-vacuous because that the right-hand side is less than 1. It is not tight, but it is non-vacuous. That tells you that the theory applies just fine. You just need to appreciate that you're not fitting arbitrary data. You're fitting data which at least has some low-dimensional structure. And you can kind of do numerical variants of these kinds of results and make essentially tight statements about how the test error behaves. Okay, so the summary of all this is that neural networks do not overfit when input data is effectively low dimensional, and the reverse is also true. When input data is not low dimensional, they can overfit.
So Q is the posterior over the weights, is that right?
You are allowed to choose Q in any which way, yes, and conceptually it is the posterior over the weights.
Okay. Yeah. So the KL should be like at least naively proportional to the number of weights.
Yeah.
Okay.
Yeah, but the point is that because it is sloppy, it is actually proportional only to the important degrees of freedom. Yeah.
I, for instance, randomize the labels, I
Mhm.
don't change the structure of the variance matrix, all fail to.
Yes.
What's, how do I understand this?
So the way you understand it in this framework is that the Q that you would be plucking out is the wrong one.
Right, but
So the
all fail to generalize now.
yes, and you will notice that this part is very off.
I see.
Yeah.
Fine.
Yeah. So I will talk about labels in a bit. There is a lot of very cool things going on the label space also. Here is a second implication of this low dimensionality of the input images. Okay, and I'll describe to you a result that we had at PNAS last year. It is titled "The Training Process of Many Deep Networks Explores the Same Low Dimension Manifold," and this is from a bunch of papers that we have had over the years with Jim Setna's group in Cornell and some of his students. The thing that makes deep learning theorists' life very difficult is that the weight space maps into the output space in a very complicated way. It's a highly nonlinear function. Nothing that you can do to look at the weights really is convincing. We have a very weird trick. And the way to understand it is as follows. So at the end of the day, you are making predictions on the labels Y for an input X. W is the weights of the network. So your goal is to parameterize this likelihood P of Y given X using W. This is kind of the canonical question in information geometry, first line of the textbook. Okay. What makes your life hard is that this is an infinite dimensional object. I can plug in any X into this that I want and I get different outputs Y. So it's very difficult to understand it. We play a very cheeky trick. Imagine trying to understand function analysis without ever taking a class. So you take a function, you discretize the function, and just think of it as a big long vector. And so this is exactly what we do. So we discretize P of Y given X on a special set of X's, which are exactly the training samples. Okay. So if you're dealing with ImageNet, ImageNet has 1 million input images. So capital N is 1 million. For every one of these input images, you are making predictions across 1000 classes. So Y takes 1000 values. And for every image, you are in charge of predicting 1000 numbers. Okay. No matter what the weights of your network are, what the architecture of the network is, at the end of the day, you need to write down for me 1 million times 1000, 1 billion numbers. And I will understand everything about what you can ever do on this data. Okay. I won't understand anything about any other data, but that's not my goal right now. On this training data, no network can do anything that I will not see in this big vector. Okay. It also has a very interesting structure if you think about it. The 1000 numbers got to add up to 1. So this is a million product of 1000 dimensional simplexes. That is the intrinsic geometry of this object. Yeah.
So am I understanding correctly that you're basically saying I have n different models P of Y?
I have one model, P sub W. I am calculating it at n different x's.
Right.
I think maybe it's a semantic difference.
Semantic,
Yeah.
Because it,
I
yeah, we can-
yeah. Yeah, if you say that the model is a conditional likelihood, then this is okay. So in this big billion dimensional space, a few points are special. Typically, when practitioners train their networks, they like to initialize the network so that it predicts 1/1000, 1/1000 for every class, for every image. So we begin training typically from near the centroid of this simplex. Okay. And typical ways to initialize the weights will actually give you the centroid up to statistical fluctuations. We give this point a name. We call it ignorant model. It's perfectly ignorant about any class on any image. This is where you begin. Your goal is to fit the one hot distribution. So your goal is to go to one of the vertices of the simplex. We call it the truth. So your goal here is to go from the centroid to the truth. What makes your life difficult is that you cannot travel in the space of probabilities. I would just draw the straight line between them otherwise. you have to take updates in the weight space. And the weight space maps into this space of probabilities in a somewhat complicated way, which is painful. So here is one question that we asked. I know this is the space in which I live. I would like to understand where typical networks live in this big space. And so the basic premise, basic technique is rather simple. I train lots and lots of networks, put them in this big space, watch what they do or where they are during the course of training, maybe after training, the thing that makes your life very difficult here is that this is a billion dimensional space. So any way of recovering geometry of this space is completely doomed. High dimensional vectors are orthogonal with essentially probability 1. So anyone who says that I can recover geometry of high dimensional spaces is lying. Turns out there is a very neat workaround this issue. Geometry in high dimensions becomes pathological if you use metrics to measure distances between 2 points. For example, if I were to think of this is a probability distribution, I would, if I took two models, two neural networks, and wanted to compute the Hellinger distance between these two probability distributions, you would get a big product over all the n images. You get something like 1 minus product over n of the inner product between the square roots of the probabilities of each image. And that product is what kills you. That is what makes the Hellinger distance boring. Things that are not metrics, that are just distances that do not satisfy triangular inequality are a tiny bit better behaved. They also become pathological in high dimensions, but they become pathological a little bit more slowly. We are fans of this distance called the Bhattacharya distance, and here is how it looks. The probabilities of every corresponding to every image, the 1000 numbers, they sum up to 1. So if I take the square roots of these 1000 numbers, they lie on a unit sphere. So the inner product between the square roots corresponding to one network U and another network V is the angle between these two vectors on the sphere. I take the logarithm of that angle that happens to be called the Bhattacharya coefficient, and then I average it over the data set. This is actually the replica limit of the Hellinger distance, and it is all very mysterious. But the Hellinger distance becomes boring when n becomes very large. The way you solve this curse of n becoming very large is actually to send n to 0. And I bet you guys have better intuitions than me. I do not have any. So, but it helps us that this is a well-studied quantity in information geometry. It is a divergence. It is not a metric, but it is interesting, just like the KL divergence is interesting. Okay, some measure of the discrepancy between the probability distribution on the space of outputs induced by network U and another network V. Given this distance now, you have defined a topology. You can take all your networks, do something like PCA. This happens to be a very fancy version of PCA that is tailored for extremely high dimensional vectors and vectors that are corresponding to probability distributions. Yes.
This is classical distribution of the
Yeah.
So how does it relate?
It doesn't actually. So Wasserstein distance is the cost of transporting across two probability distributions. This is another distance. So distances don't have advantages, just like norms don't have advantages. So just like there is no favorite norm that you should be using. 2 norm is as good as 4 norm, as good as P norms. The way I personally think of this is that some distances are useful and some are not. So what you are after is studying the geometry of the object. You're welcome to use anyways distance. This one we like because we can say something about the isometry of embedding from the space of probability distributions to a lower dimensional space. If you were to do this whole exercise using Wasserstein distances, you would be able to do it technically speaking, but you wouldn't be able to interpret the embedding as easily. Does that make sense?
Well, if you change the distance, you change geometry. So
You change the geometry, and the question that you Exactly. So you change the geometry, but now but the reason we are discovering the geometry, or we are studying the geometry, is to make some qualitative statements about the phenomena. So if we can make those statements with this new geometry, that's just fine. So moral of the story, we basically do principal components analysis with this distance matrix. It is called multidimensional scaling, a much older word for these kinds of things, but basically this. The cool thing that happens technically is because we are not using metrics to compute distances between points, triangle inequality is violated in the big space. So when we do a projection, if we want an isometry, we also have to violate triangle inequality in the embedded space. So we actually have to embed things into Minkowski spaces, and that's just a theorem. But it is kind of cool because MDS, multidimensional scaling, is very popular in bioinformatics. They will take their genome sequences and come up with distances between these and do basically very similar analysis. And they go through lots of contortions to escape the negative eigenvalues. But the negative eigenvalues are real. They really, they're imaginary, but they are real. They really come from the fact that we are using specific distances in the original space. Yeah, yeah. You can symmetrize it, and we also have studied things like symmetric KL divergence, and that gives you a different qualitative picture, but the essential phenomena stay the same. Yeah. Yes, I can. Give me a couple minutes. So here is a result. This is the first 3 dimensions of my fancy PCA. Every point is one neural network. There's many different architectures that are being shown here. So there is 6 different architectures: fully connected networks, CNNs, VITs, ResNets. They were trained with many different algorithms: SGD, Nesterov acceleration, ADAM, different learning rates and batch sizes and weight decay and regularization and different initializations. There's about 150,000 points, 150,000 networks, corresponding to about 20,000 configurations. And then I checkpointed them 60, 70 times during the course of training. P0 corresponds to what we call ignorance. This is the uniform distribution at the centroid of the simplex. So all these networks, by design, they begin training there. We also chose these networks to make sure that they have exactly 0 error at the end of training. And what I'm showing you is what paths they trace as they train. Yeah, you don't see them hitting exactly the vertex of the simplex because this is Minkowski space and the second eigenvalue is complex. And so there's a light cone and they fall on the sides of the light cone, blah, blah. But they do hit the vertex. They do have a small distance with respect to the vertex. What is very peculiar about this picture is that the configurations of these networks are very different, architectures are different, optimizers are different, but they all seem to travel on rather similar manifolds. We know that they ought to predict the same thing at the end of training because that is the hard distribution that is selected for, but they also predict the same thing along the way, which is very weird. The CNN and the VIT look very different. The ResNet is again quite different, but they behave similarly as far as the training trajectories are concerned. You would think that if they're all so similar, maybe this is also the right thing to do, but not quite. So you can compute the geodesic analytically in this space, again, because it is product simplex. They don't take the geodesic. Doesn't mean that the geodesic is a good trajectory to take always. It just happens to be a short trajectory. But they stay away from the geodesic until it suits them to come close to it, because the geodesic also hits the vertex, right? The most important thing I think to take away from this picture is that this is a faithful representation of what is going on in the big high dimensional space. This is CIFAR 10 because this picture cost about $50,000 to create. For ImageNet, multiply that by 10. So we haven't done it for these many models on ImageNet, but CIFAR 10 has 50,000 images. So 50,000 times 10 outputs, 500,000 dimensional vectors that are being embedded into these 3 dimensions. And these 3 dimensions capture about 76% of the pairwise distances in the big space, which is very stark, because that tells you that the large ResNet, for example, has 50 million weights. The red network here has 1.5 million weights. And these are such redundant parameterizations of this very low dimensional intrinsic manifold that these networks ought to live on. If you give me 50 dimensions, I couldn't plot it, but I would be able to capture the pairwise distance between the points essentially perfectly to 98%. So this is really like evidence that there exist very, very succinct architectures. This succinct, it's a computational proof, if you will, that there exists an architecture with 50 coefficients that reproduces the predictions of all these networks on the training points. And the same thing is true for the test data also, okay? So this is not as if there is something peculiar about train versus test. This is really how starkly low dimensional the optimization problem in deep learning is. We just happen to see the very ugly version on our computers. What we did recently is it seems very surprising. And if I could train with these 50 coefficients only, then I wouldn't be talking to you guys. I would sell myself to Sam Altman and be done. We are trying. We recently proved that this low dimensionality arises because input data is low dimensional. It technically arises for 2 reasons. When input data has sloppy structure, and when you initialize neural networks with a very small variance near the ignorance, these 2 things control the dimensionality of the manifold that you're looking at here. And this is very important to appreciate, because natural data is natural data. We are happy that we have this low dimensional data. But roughly 10 years ago, when practitioners in deep learning were not very good at using deep learning, we did not initialize our weights carefully enough. And the replicability of your training process was nowhere close to what you have today. Today, every one of us can train a neural network just fine because PyTorch magically initializes things. It wasn't the case before. And so what is really happening here is that the big billion dimensional space is really vast. So if any VC bound, any way of characterizing the complexity of this function class is completely doomed, you will never ever generalize. You need lots of samples by the curse of dimensionality. The thing that is happening here is because you choose initialization in a small ball, you actually span a very, very tiny subset of this big product simplex. And actually, the complexity of the functions that you explore is much smaller than what you could have explored. So natural data protects you from having to explore this vast space. This is why networks generalize. And so we have formal calculations of these phenomena. We can prove that the volume that you explore in the function space is really very small. And that is what gives you generalization in deep learning. But really, it comes from the fact that your data is low dimensional. And let me just go directly to the last slide. You have no idea how many I skipped in between. I would like to contend that the magic of deep learning is really the magic of just data. Typical inputs are low dimensional. And what I skipped actually was the fact that typical tasks are also somewhat simple. I can tell you later how. And this is really the 2 driving forces as to how why you are so successful. We are not counting leaves on a tree. We are not giving names to stones on the road. We are saying we are making very obvious inferences. This set of pixels is called a cat, and happens to be something that was chosen by humans so that we became good at classifying it, and the networks also behave in the same way. And just to conclude, I am trying to build more efficient architectures that exploit these structures. And if we are successful at it, you should be able to get very, very efficient training regimen and smaller architectures. There's a flip side of this. You have heard of words like test time compute and scaling and thinking and all these things. If we think of these results in that context, I am claiming that deep learning works well because the tasks are somehow simple. Where does deep learning not work well yet? it gives you 75% accuracy when you build an object detector. Classify or detect objects in this room. I do it with 75% accuracy. Well, you and I do it with 100% accuracy. So if I were to tell any of you that there is a stapler in the room, you will find it. Maybe not immediately, but there is one. The goal of inference is to really get 100% accuracy. And so if you're not going to put any limits on the amount of data we use or the size of the networks, then I, as a user, really want 100% accuracy. I am not happy with 75. If you want to give me 75, give me a network which is 1,000 times smaller. Okay, I'll stop there. Thank you.
Doesn't look like a stapler. Anybody want to? There are the rare things in the database, doesn't mean they're not important.
No, they're yes.
Algebra could be rare compared to the amount of
Yes,
data.
yes.
So how much of this low dimension manifold is, let's say, in an image setting, I can think that, so if it's Fresnel eigenvalues, I would track the bias, the linear terms, some very simple contrast things, but that would only take me so far in terms of performance. Actually, the more interesting, nuanced, smart things are happening outside.
Exactly. So this is really the point, crux of the things. The problem that we are solving is ill-conditioned. It has a condition number of 1 billion. In the tail of this problem lie these rare things that we want to classify, right? The networks are good at it. Why are they good at it? Well, because the large dimensionality gives them a good overlap with that subspace. So the probability of you initializing close to solution is larger because of over-parameterization, but that doesn't really save you from having to dig through this eigenspectrum. The low-dimensional models in scikit-learn dig through the head, the networks dig further. But yes, we like the 95% accuracy and we don't like the 90. The extra 5 is the tail. Yeah.
Actually, can we pause for lunch and you guys can
Cool,
interrogate
yes.
as we go, as we eat? Okay, thanks a lot.
Thank you.